Hello, my name is Christian Lee, and this is my video for Lab 1. Introduction. The purpose of this lab is to analyze the motion of an object moving at a constant velocity. We will plot the position of this object over time on an xy coordinate plane. Afterwards, we will attempt to predict the position of this object using a computational model, then plot that on the graph as well. Why is this important? Well, this lab exemplifies Newton's first and second laws of motion. Newton's first law of motion states that an object at rest will stay at rest, and an object in motion will stay in motion unless they are acted on by an outside force. In our lab, this object is already in motion, and thus does not need an outside force to stay in motion. Newton's second law will later be used to predict the position of this object. Let's watch the video. Alright, now how does Newton's second law apply to that? This law is most commonly known as form F equals ma, or net force equals mass times acceleration. Acceleration is change in velocity over change in time, or delta v over delta t. Now, what's important to note about this is that delta v is the difference between final velocity and initial velocity. Now, in the case of this lab, final velocity and initial velocity are the same, since it's constant. This means delta v is 0, which means acceleration is also 0, which means net force is 0. Now, even though net force is 0, there are still forces acting on this object. For example, in the y direction, a gravitational force pulls or pushes the object down. Meanwhile, a normal force pushes the object up in an equal but opposite direction. The gravitational force and normal force cancel each other out, resulting in no net force in the y direction. In the x direction, friction and air resistance are neglected, thus no force is applied in the x direction. This makes the velocity constant. How are we measuring our observed position? Well, we put our video into Tracker. As you can see here, these data points follow the ball's position over the course of the video. These data points are plotted in this table here, which includes the time and the position of the ball. Now, there's a human error present in Tracker because these data points are selected manually. This means that there's a lack of precision in the position of the ball. Now, to predict the position of the ball, we must first calculate initial velocity. This can be done by taking the first two data points here in Tracker and dividing the change in position by the change in time. This results in a velocity of 0.935 meters per second. We can use this velocity in our position update formula here, and let's look at that in GlowScript. Alright, so we can see here that the ball's velocity is 0.935 in the positive x direction. Meanwhile, the net force on the object is 0. Now, here's our position update formula, and let's look at this in action. Wow! So as we can see, the position versus time graph is linear. This is because the velocity of the ball, or the slope of this graph, is constant. You can see that here is a constant 0.935 the whole time. Now, these data points are recorded in this table here, which we will use to graph these lines. Let's take a look at that. All right, so the blue line is the actual position of the ball we got from Tracker, and the orange line is the predicted one we got from GlowScript. Now we can see that as time goes on, they begin to diverge, and our prediction gets less accurate. Why is this so? Well, there are some assumptions and flaws in this lab that are present from the very beginning. The first is that we assume there's no friction or air resistance. This is of course not true in real life, as in real life there are these forces that are pushing the ball in the negative x direction and thus slowing it down. Another assumption we make is that the ball is perfectly circular and the table is perfectly flat. This is because any imperfections in the shape of these objects results in non-constant velocity. Another assumption is that our initial velocity we calculated is actually accurate. This we know is not always the case because Tracker has a lack of precision due to us manually selecting the data points. Lastly, there is always going to be human error present in these labs. It could be the way the ball is rolled or the angle of the camera. How can we improve this model? Well, we can solve the problem of an accurate initial velocity by instead using the average velocity. Now, we can do this by using the first and last data points on Tracker, and we can see here that this prediction is much more accurate. However, there is still a discrepancy in the middle here due to the other assumptions we made earlier. Alright, now what would happen if we flipped the x-axis on tracker? Here, right now, we have the positive x-axis pointing to the right. What if we switched it so that the negative x-axis points to the right? Well, then the ball will be moving towards the negative x direction instead of positive, and thus the graph will be flipped over the x-axis, or reflected over the x-axis, and it would trend downwards instead of upwards. This is the same principle applied to average velocity, and it still trends downwards. That is my video. Thank you so much.